Welcome once again. Tonight's topic is another in our series on solving technological progression problems. I don't think we're progressing fast enough. I think we could be doing better. We seem to be in a rut. And tonight's topic is on communication. As I just mentioned, this is in a series. Tonight we're doing communication. Now, all current communication is based upon modulation of the electromagnetic spectrum. And we need to transition away from that to other things, maybe gravity wave, maybe other things. And then next week we'll do transportation. So yes, some of these things are conceptual, but they draw upon scientific principles that are from noteworthy folks. Some of them are Nobel Prize winning research. It's repurposing. So you may think of, well, that's not what that was meant for. Why not repurpose it? Envision what it can become over time. I was looking at a magazine that I read on medical devices, and it was showing how antique medical devices just in the last 50 years have changed with all the advances in electronics. And, you know, the latest issue of the AARP flyer had in the back of it a picture of a radar range microwave oven. So if you saw one of those when they first came to market versus what's available today at your local store or online for under $50, that's what we're talking about here is put some money in it, make it better. You're going to sell more, you're going to do more if it's better. So make it better. So these are obviously not yet commercially at scale products. You're not going to be able to go buy one off the shelf and just push buttons to get a solution. There's going to be some required skills, some required learning, training, understanding, and then maybe a little do-it-yourself. But if you start with the premise that it's possible as opposed to impossible, and do understand the contemporary information that's out there, maybe some of it Nobel Prize winning, and then reassess before coming away with things like, it violates all the known laws of physics. Well, maybe. Then again, maybe those known laws just are not what we're talking about here, not applicable. We looked at that in propulsion, how Newton's third law is not the basis of that propulsion mechanism, but there are other things that it is based upon that are proven science. Just as there's considerable investment in things like fusion, particle physics, like the Large Hadron Collider, and billions spent on quantum computing. We have access to things like nanoscale fabrication. So let's spend some of the, slice off a few million of those multiple billions to invest some money in other areas. Maybe things will progress. So tonight we'll talk about communication. People don't think of communication as having a problem. I just pick up my mobile phone, I call people, what's the problem? Well, all communication is based upon the electromagnetic spectrum and modulation of it. By modulation, I just mean you turn it on, you turn it off. That's modulation of the energy of the electromagnetic spectrum. And that comes down as simple as telegraph key. That's the simplest form, turning the current generation or the audio generation off and on. Ship semaphore lights, the little flappers they use. Well, nowadays they use lasers and they turn the lasers off and on, but it's still, modulation of the electromagnetic spectrum. All radio communications, Bluetooth, Wi-Fi, all that stuff is literally high-speed, selective wavelength, turning the energy off and on. And even lasers, when they go, it's not radio, it's lasers. Lasers are just a different wavelength of the electromagnetic spectrum, and they can just switch them off and on very, very high speed. And they don't just use ones and zeros, they actually use phase modulation. So as the signal is ramping up, they call that a bit. When the signal gets over the top, they call that a bit. When the signal gets down over the trailing edge, that's a bit. When it gets back down at the bottom, that's a bit. So you can encode in what is known as trellis encoding, 64 bits in a single sinusoidal waveform. And if you remember back in the day when modems, dial-up modems, made the gigantic leap to like 9,600 bits per second and above, that was when we stopped encoding single bits on single waveforms, and we started using phase encoding to encode a trellis of multiple bits onto a single waveform transition. So they can do all kinds of fancy encoding, but the end result is you're just still turning things off and on. So what do we have access to with modulation? With modulation, we can increase or decrease the signal, that's amplitude. We can change how often we're changing the signal, that's the frequency. The phase, as I mentioned, as you're ramping up over the top or ramping down, we can do that. We can do quadrature, that's another kind of form of trellis encoding. And then we can lump it all together and do, some amplitude, frequency, and phase all in one modulated signal. And this is how the deep space probes work, because they need to ensure that all the data makes it across. So they not only give you the data, they also give you checksums and correction codes. So even if you drop out a bit or two, you can get back the original data. But there are other things besides the electromagnetic spectrum that you might be able to do that with. The electromagnetic spectrum communication suffers from common things like stuff getting in the way. The sun gets in the way. You can't transmit EM through the sun. Solid things get in the way, like planets and moons. But even if you're on the ground, foliage, that's, trees and branches and stuff, and structures, buildings, antennas, and poles, all those things get in the way. And if you don't think that's the case, if you wind up subscribing to SpaceX Starlink and you put the dish up on your roof and there happens to be a tree over on the edge of your property line that you can't cut down because it's actually your neighbor's tree, when the dishy wants to point that way, the signal will be blocked. So stuff gets in the way. You have conflicting signals, stuff that's at the same frequency or wavelength as what you're trying to send encoded signal on. There's general light pollution. Well, there's general radio pollution, just artificial hash background noise from all kinds of things. Internal combustion engines have spark plugs. The sparks are essentially radio transmitters, and that's why they put a capacitor in line with the spark plugs to get rid of the radio frequency emission of automobiles. How many automobiles? Thousands of automobiles near your radio receiver are all creating noise pollution in the radio level. And then if you're doing it for military purposes, there's deliberate jamming. And then there's the unavoidable stuff that if you want to transmit at a certain band of the electromagnetic spectrum, the solar wind gets in the way. The interstellar winds from other stars get in the way. And then the cosmic background radiation gets in the way. So you're narrowing down or dividing into channels where you can and can't communicate. And then it suffers from distance issues. As your distance from your transmitter to your receiver increases, the electromagnetic spectrum energy spreads out, and that means that your receiving station is going to get less and less energy. So your signal to noise, how far above the background noise level your intended signal is, your signal to noise is going to drop off, and you won't be able to as easily pick up the signal you're looking for. And as you get farther away, that background interference starts to distort the signals. It doesn't just get in the way of them, it actually shifts the frequency of them. So you get attenuations and phase shifts. And when you get out to billions of miles or maybe light years distance, it starts to take time to get the signal back and forth, because space is not a perfect vacuum, so you're not moving precisely at the speed of light. You're moving just a touch less than the speed of light, and you get all sorts of distortions. So when you think about space probes like the one that went to Pluto, they're not talking about gigabits or megabits. They're talking about small numbers of kilobits in order to make the bits fat enough, take up enough time domain so you can clearly detect the waveform in the signal. But if they tried to transmit gigabits, you'd get, a small fraction of the total bits. So these are all problems with electromagnetic spectrum modulation. Now, we can only pump out so much power so fast. So if you're talking about, I want to transmit to another planet in our solar system, you're not going to send gigawatts of power through the Earth's atmosphere. There's a lot of countries that don't want you cooking their atmosphere. And there's only so fast you can switch it. We're now down into the femtoseconds. And if you think about it, there's nano, which is a billionth of a second, and there's femto, which is a thousandth of a billionth of a second. So we're switching it rather fast. I mean, there's attoseconds and exoseconds and all kinds of things beyond there that we've mathematically looked at and used in laboratory studies, but we're not doing that on even military radio at this point. And it's not always that you can use the cross product of these two. You can't just crank more power into an existing frequency signal. You may have to adjust the frequency because you're using more power. And faster switching requires faster power, requires more power, but you have to reduce the power because you then start to force the edges of your signals and it gets distorted. And it's all based upon electrons generating photons. And where that comes in is if you talk about lasers for communication, that's essentially you're taking electrons and using those to stimulate a material to generate photons. And then you're selecting the photons you want that are all going in the same phase coherently out of direction. And then you're switching it off and on very quickly to modulate that light beam. But all of our radio communication involving electromagnetic spectrum requires a photon to electron conversion. This is the photoelectric effect that Einstein has papers on, as the saying goes. There's time required to do the conversion from photon to electron, so that's going to limit how fast your signals can be. And that's where we're kind of stuck at femtoseconds, is we're nearing the limit on how long it takes to do that conversion. And then when you want to do the conversion, you're going to be taking photons, radio waves, light waves, and converting those into electrons in basically a well. And then you store so many of those over a period of time. And then you call for those electrons to be piped out of the cell. And then they'll run across what is known as an analog to digital converter, an ADC, that will be converting that quantity of electrons into a measured voltage. So how fast can you drain that out and go through the analog to digital converter, which is a resistor ladder. So if the voltage is of a certain level, it will pass up through the ladder of resistors a certain level and then exit. That tells you it's at least this many volts. If it's fewer volts, it'll be through a lower resistor. And each of those resistors is directly connected to the mapping of a digital value output from the analog to digital converter. So how fast can you do that? Well, you're moving a lot of stuff through circuitry, so you're going to be time stretched for how fast you can do that. And right now we're at the femtosecond level, and we're not going to get faster sooner without changing some things. And then there's, you probably heard of, when you talk about analog to digital conversion, it's how many bits, how wide is the digital value? Is it 8 bits, 12 bits, 16 bits? Well, the more bits you want, it makes the ladders taller, so you have more resistors, so the voltage has to move up and down that ladder array. So it takes longer. You're not going to be able to do, a femtosecond measurement of frequency using a 32-bit analog to digital converter. It just can't get the energy moving quickly enough. So you're going to have to cut that down and say, we're using 8 bits because that way we can do femtoseconds. So our current approach is to staying with electromagnetic radiation modulation for communication. How do we stay there? We want to stay in that rut because we get a lot of proven stuff, a lot of vendors that can make bits and parts and pieces for us. But how do we get it to work better? Well, make the transmitters higher power, obviously, crank up the wattage, higher gain antenna designs, do that cryogenically cooled receiver, larger dish antennas, more of them, put them all over the surface of the earth. Through regulatory administration, have radio quiet zones to, you can't use that cell phone here, it's going to disturb the VLA kind of thing. We join multiple radio antennas around the planet to get very long baseline interferometry. We design through semiconductor circuitry lower and lower background noise receivers, make those analog to digital converters as fast as we can. How fast we can switch them. We use, like I said, multiple forms of modulation. We'll do amplitude, frequency, phase, trellis encoding, and then bit error correction, all in the same signal. As the saying goes, overtick the plumbing. And we need higher frequencies to transmit more information, more transitions per second. If your frequency is only kilohertz, you're not going to be transferring gigabits worth of data. You need something that the frequency is in the multiple times gigahertz to transmit gigabits. And you have to transmit slower over longer distances to improve that signal to noise ratio so you can get out those distances to Pluto. And there's a diminishing return. The longer you want to stay with it, the more you're going to have to just go, well, this is what we got. We're not doing anything fancier. We're not, think of anything new. So we have to live within these constraints. When you send a spacecraft out to like Jupiter, if you're not going to be using radioisotope thermoelectric generators based on plutonium, because plutonium be radioactive, and that's a problem, scary for people. So you've got to, cut it back to how big a solar panel can you stick into your spacecraft, and that fairing at the top of the rocket. That limits you as to how much power budget you have, which says how strong your transmitter can be, how much amplitude modulation you can do on your, decoding on your receiver. Maybe you use cryogenic cooling, but if you don't have the right kind of systems, that stuff leaks out, and it might only, you might be out of cryogenic cooling after about 5 years. We can only make the antennas so big because they have to fold up inside the spacecraft. And if you remember, the Galileo space probe at Jupiter, when it went to unfurl its giant parabolic dish antenna, it said, unfurl, and it went, ah. It didn't go, ah, it went, ah. So they had to reprogram the space probe for a lower data rate because that's all the signal they could get. So we can only make antennas so big on Earth before it just becomes unsightly for some folks. And, we're spending billions on the Hadron Collider. We're not going to spend billions on antennas. And anything that's that big an antenna, it will not be equatorial because the counterweight masses just get to be silly. So they're all altitude azimuth. So there's signal rotation, which can affect the phase. And we can only switch so much power so fast for transmissions. The analog to digital converters can only decode so fast. We can only find so many mountain enclosed buckets to put antennas, separated by 50 or 100 miles from the nearest city, like the VLA is. You can only make the long baseline arrays so long before you run into curvature of the Earth. If you say, I've got a long line of antennas, no, you don't. You have a curved arc of antennas. And well, they can point down just so low to the horizon before they start getting interference from the atmosphere, the atmospheric distortions of the Earth's atmosphere, humidity and such. So your very large array can only get so large. And you've got a space problem as to where can you put them. Cities get in the way because every so often there's a city. You need to reserve bands through regulatory action to get rid of some of the noise sources. But if it's a natural noise source, there's no amount of government regulation that can make that go away. So what they do is the farther probe gets away, the lower the data rate, the more convoluted the signal, just so they can stick with electromagnetic radiation modulation. So if we wanted to create a better solution, here's how we go about doing that. We want zero RFI, be it artificial or man-made or natural. We want no interference. We don't want it to be obstructed by anything. We want whatever signaling we're using to go through buildings and trees and atmosphere of any kind. And, when the moon gets in the way, we're going to signal right through the moon. All of these sound like impossible requirements, but if you could have your best of best solution for replacing electromagnetic radiation, this is the kind of things you'd want. You want unlimited data bandwidth over vast, maybe interstellar distances. You want your gigabits. You don't want it to take forever. You don't want to have to worry about deep space communication and a reliable signal to noise ratio. You'd like it to be as close as possible to the speed of light, c. You'd like to find a way for it to be what is known as superluminal, greater than c if that's possible. And I'm not talking about subspace carriers a la Star Trek. But what it does require is a paradigm shift in communications principles. You've got to get off that bandwagon of electromagnetic radiation modulation. So we're going to involve multiple mediums for this. So we're going to say, we've got to generate a carrier, background signaling. We want to be able to modulate it to encode information in our signal. Demodulated, that's decoding the information from the signal. We've got to have practical deployment for each end. It can't be like, well, it'll just take an Earth diameter antenna to pick this up. It's got to fit within the available space. It's got to fit within a rocket. So, on Earth, the thing can be bigger, but on the space probe, it's got to fit inside the rocket, and it can't weigh, like kilotons to do this. It's got to, be able to be something you can launch. And if all you have are solar panels and you're out at Jupiter or beyond, it's got to fit your power budget. So it can't be, gigawatts of transmit power. And it's got to be something that you can fabricate, build, make, install, and operate for, less than a king's ransom. So we won't have an open-ended budget for doing this. And, it can't take forever to build this stuff. It's got to be some physics principles that we already know about. And it must not be dependent upon electromagnetic radiation modulation. I'm sure it'll probably be dependent upon analog to digital converters at some point in the process, but it can't be radio, it can't be lasers. But we've got to be able to spend some money to get to this. So we're going to have to spend some money understanding what other things can we modulate? Can we create a carrier with? Can we demodulate? And we're going to have to go through, engineering models, testing, put some universities to research money, optimize them, build some prototypes, test it out on a short range, mass produce them. And if you think that we haven't done this kind of thing before, there was a space probe called Deep Space One, and we lumped 5 different unproven in deep space technologies. Ion propulsion was one of them. Modulation for deep space communication was another one. Deep space solar panel power, radioisotope thermoelectric generator power, the software for complex multiple body navigation. All of this went into this one program called Deep Space One. And you know what? All of those technologies are now just take it for granted givens. So talk about ion propulsion. Well, yeah, that's how Dawn got from target to target. Ion propulsion. Every SpaceX Starlink satellite uses ion propulsion for its, keeping on its station and moving around. So these things start out as, hey, what about this? And then everybody laughs at it for a while. And then after about 40 years, they go, it's got some merit. Let's try that out. And they get the funding and they try it out and they go, well, may not be the greatest thing since sliced bread, but it's a different way of doing things. And sometimes that's better because some of those constraints and restrictions fall by the wayside. So if you said, I'm going to use a combustion rocket fueled craft to take me on a cross the solar system trek to stop at 3 different asteroids, you won't have the fuel to do it, because when you turn it on, it wants to burn all of the fuel immediately until you turn it off. Well, that's where ion propulsion comes in. You can run it at very low throttle for very long periods of time, and collectively it will push harder and harder and harder on the craft and get you there. And then you can go into orbit around that one using traditional chemical propulsion. And then once you're done there, you can turn on the ion again and do it. So you've got to have the faith to see that there's a possibility for repurposing some of this stuff, using the underlying scientific principles that we already have to do new things with it. Considerable research and development money will be required. None of this is off the shelf yet. Remember, we're not using radio frequency or light. Came up with 2 things: high frequency gravitational waves, because we know those things travel across basically the universe, certainly the galaxy, certainly our meager solar system, and these very distant sources of energy called tau neutrinos. Tau neutrinos are believed to be neutrinos generated at the beginning of the universe, back during the Big Bang. They're they're millions of times more energy than electron neutrinos from our sun, or even weaker neutrinos from our nuclear reactors, our fission reactors. So this is a very exotic form of neutrino, but very, very high energy, and they come clear across the universe. So here's 2 things that very high energy, and they seem to be a signal that already exists. So the natural physics of them says they exist. So all we need to do is find out, how do we cook them up? How do we create them? And then how do we modulate them? But there's your 2 approaches to getting off the addictive electromagnetic radiation spectrum stuff. First, we'll talk about high frequency gravitational waves, or it's got an acronym, and I didn't come up with it, HFGW. There's actually a proposal from 2018 talking about gravity waves and the fact that there is a whole category of gravity waves that we're not detecting yet. The gravity waves that we are detecting are high amplitude, very low frequency gravity waves. These are LIGO and Virgo, the big L-shaped things. They're coming up with new gravity wave detectors that are physically much smaller, will basically fit on a tabletop, because their detectors are many, many times more sensitive than LIGO and Virgo, because technology is advanced. We do, critical cooling of things. But we can now detect higher frequency gravity waves. And what that means is a gravity wave that's shorter in duration, lower in amplitude, and they're just like there and gone, because unless you catch them as they go by, you never saw it. But they pass through obstructions. The only 2 obstructions they don't pass through are the cores of stars and black holes. The gravity is just too great, because they're, after all, gravitational waves. But they're less affected by particles that are roaming around in the vacuum of space, so to speak. So they'll propagate closer to the speed of light than even laser light moving through the galaxy. They're good for interstellar distances because they're not affected by the cosmic microwave background radiation. Current research is creating smaller, higher frequency gravity wave receivers. And when you can do higher frequencies, you can start to detect more. It's believed by the people who are saying, you'll never get that to work, that you have to have massive amounts of power in order to create the necessary carrier wave or high frequency gravity waves. And to that, I would say, you do own a cell phone, don't you? Cell phones at 5G are transmitting very fast in the gigahertz range, and it runs on a lithium polymer battery that you recharge overnight. So just because you're communicating doesn't necessarily mean you always need high power. if you can find a way to generate more efficiently, more effectively, maybe it doesn't take as much power as you think. There is currently no meaningful research into high-frequency gravity wave generation, only in detection. So once we can detect high-frequency gravity waves, and we have multiple observatories or observing sites doing this, we may find out, as they predicted, that there is a cosmic gravity wave background from the original formation of the universe. So much like there's a cosmic background microwave, there may be a cosmic background gravity wave. So that would be a frequency where we're not going to transmit and receive in that. There's too much noise, natural noise. So we will have to think about what frequencies of gravity waves we can do that at. The second approach will be tau neutrinos. And if you want to find out about tau neutrinos, there's links to information. There is actually a 2015 Nobel Prize in Physics for the fact that neutrinos come in multiple flavors, which they kind of already postulated, but the fact that neutrinos, without any effect from us silly humans, change flavors on the fly. So if a neutrino comes out from the sun, it may start out as a meson muon neutrino, and then switch over to being an electron neutrino. And if they are energetic enough to leave our solar system, they would certainly be tau neutrinos. So for whatever reason, they're doing this on their own. And the only way you can shift energy is if your particle has mass. Another aspect of science, proven stuff. So if you're changing energy, there's got to be some mass involved. And the way that they measure the mass of a neutrino is pretty much the way they measure the mass of a moving photon. They measure it in electron volts per speed of light squared. We get to other units of measure, but it's basically all down to electron volts. And it takes a lot of electron volts to make one, as we refer to it, layman's volts. But depending upon whether you're following the Dirac or the Majorana mechanism for switching the flavors back and forth, the mass is going to be minuscule. But if you remember back in the presentation on power by neutrinos, there are billions of neutrinos from the sun, electron neutrinos, passing through the fingernail of your little finger every second of every day, day and night. So even though individually they're very low energy, collectively, if you can catch more and more of them, if you can modulate more and more of them, you now have a valuable source of signaling. We've detected tau neutrinos in linear accelerators. The Stanford linear accelerator, Lawrence Berkeley Labs was running at the time. Fermi National Labs, they've done it. These things pass through obstructions. So if you think, I'll just put up my lead wall, that'll stop them. No, tau neutrinos will go right through your lead wall as if, what wall? I didn't see any wall. So you've got your particle that can go through pretty much anything, but not stars and black holes, because they are affected by gravity. Because they're not affected by radio, they'll travel much closer to the speed of light. They're good for interstellar distances, again, not affected by cosmic microwave background. But again, people believe it takes enormous sums of power to generate tau neutrinos. Yeah, but also there's a lot of them, so individually they can't take up that much energy to produce them. And our only detectors are indirect via EM, not optimal. So if you think about, well, how do we detect a tau neutrino? We detect it through radio waves. The radio waves are photons, and then we do our normal decoding, but we're just detecting them. We're not demodulating them. So we're not pulling a signal out of it because we don't know enough about them. Large-scale generators are currently believed to only be natural. humans will never be able to make a tau neutrino generator. Okay. And we'll never be able to produce photons of high, gigawatt levels in femtoseconds. So if you never say never to your people saying never, then maybe there's a way. But, it's impossible. Well, there's a lot of things that were impossible that aren't impossible anymore. And most of those things are currently in your mobile phone. We have been able to generate tau neutrinos unexpectedly in limited quantities with a limited life in particle accelerators. But that's not controlled enough where we can modulate it. Since tau neutrinos make it all the way across the universe, there is currently no known cosmic interference sources for tau neutrinos. So once you can generate them, once you can produce a carrier and modulate them, communicate anywhere and anywhere, nothing gets in your way, not even planets. Okay, some foundational information. How would we generate gravity waves? As far as we know it today, gravity waves are generated by the movement of large masses. And LIGO and Virgo think of large masses as neutron stars orbiting one another before colliding and to become a black hole. That level of energy is what we think of as what it takes to generate a gravity wave. But that's only because our detectors are so anemic, inefficient, that it takes that much energy just to get our attention. What other kinds of things are large masses moving that occur all the time? Mass dampeners in tall buildings. If you remember the history of the Hancock Center in Chicago, when that building was first built, they just thought putting cross struts on the outside of the building, that'll keep it from swaying around. And what they found out was, no, if you put some multi-ton weights up in the upper floors of the building, just down from the top, and you put those on slides, as the building wants to go too far that way, the weight will build up momentum and drag you back the other direction. So it dampens that out. Now you've got something that's moving multiple tons, probably a slow frequency, but once we can get our gravity wave detectors to be high frequency enough and sensitive enough, we may find that we're going to have to stop using mass dampeners because they're generating all kinds of artificial gravity wave noise. And if you can get them sensitive enough to that, imagine, a 70 tons worth of semi-trailer moving down the highway and all of a sudden needing to come to an abrupt stop. That's a lot of mass moving quickly and then suddenly moving slowly. Will that generate a gravity wave at the high frequency, low amplitude level? It might. What about a passenger or freight train? That's certainly a lot of mass moving. Now, the passenger train will probably stop quicker, but the freight train will have far more mass. What about just your garden variety, two vehicles in a head-on collision? That's a lot of mass moving together. So as we be able to detect higher frequency, lower amplitude gravity waves, we may find that there's all sorts of noise out there. And for communication, we may have to say, well, the frequency's got to be really high and the amplitude's got to be above a certain signal to noise threshold before we can use that productively. When we want to signal something and we want to modulate it, we turn on a power source and we generate that signal. That's how fast the amplitude, how fast the signal rises. So we have to be able to control how much mass we're moving to generate that gravity wave until we find some more clever way other than moving masses to generate gravity waves. And the frequency is constrained by how fast we can move that mass back and forth if we're using masses to do that. What's the shape of the actuator for a mass movement? Because we've got to go from stopped to starting to move to, okay, we've got it up to speed. Now we want to vary the speed. We want to oscillate it to create a frequency to modulate a signal. We've got to be able to do that kind of stuff under computer control, as usual. So there's foundational stuff here for gravity waves, but we've got to create some new technology. What about the foundation for neutrinos? Let's just start with neutrinos before we get down into tau neutrinos. Currently, there are no good high flux, high density, reliable, long duration sources of tau neutrinos. They're all unexpected, fleeting, and short duration. Fission reactors make electron neutrinos like the sun does. So we're not talking about electron neutrinos because even though they're neutrinos, they can be stopped by very high density things. Particle accelerators can generate tau and other types of neutrinos, but as I said, the flux is very low and the lifespan is very short. We need a dramatically greater flux, a quantity per second. We need them to be long-lived, so we need high energy versions of it to create a carrier for our communication. And we need to be able to switch them off and on very quickly for our modulation. Something they said, back when radio was just a spark gap generator, who envisioned gigabit communications via radio? So like I said, LIGO and Virgo are really great. They've detected, confirmed gravity waves from very large high energy cosmic sources. So they're very high amplitude and very low frequency, like black hole formation, neutron stars, those kind of things. And the detection is actually indirect through interferometry, and then we use analog to digital converters to do the readouts. So it's measuring a beam traveling down a very long tunnel with a mirror at one end and a light source at the other, and it's measuring the round trip travel time. And the way it does that is the beam goes out, it knows the beam's going to hit the mirror and come back, so it literally starts a clock. How long did it take for the beam to go from there to there? Well, how do they know when they got the beam back? By the analog to digital converter. It takes the photons, converts it back to electrons, and goes, yep, got a detection. Well, when the length of that tunnel gets enlarged or shrunk by a small fraction of the width of a human hair, that means a gravity wave passed through. So we've got to have something a little more capable than that in order to do gravity wave modulation. What about our detectors for neutrinos, for tau neutrinos? There's this lovely thing called the IceCube in Antarctica that we talked about, that they have detectors, but they're still using vacuum tubes because they're really stuck on photomultiplier tubes, because the actual signal, the actual light conversion to an electrical interface is so small, they've got to ramp up the amplitude to get above the signal to noise ratio just to say, we got one. But they can improve them. But it'd be nice if they used different detectors like lithium niobium or lithium niobate in the compound that generates electrons. And we'd be talking about electrons, not photons. And from that, we can generate electrons. If we can generate electrons, now we can have a digital value through our analog to digital converter. So now we have a way of doing this, but because there's other types of neutrinos, in order to just get the tau neutrinos at the highest level, we may have to clip off all the lower energy stuff at the bottom, use software filtering to get rid of the noise level. We do that in software-defined radio all the time. Get rid of the noise floor. So what kind of gains, what kind of improvements can we talk about when we start doing things more optimally? Well, we can get a higher amplitude than LIGO and Virgo. If we can sample faster, we can get a higher frequency of gravity waves. And remember, there's this guy called Nyquist that says, if you want to capture a frequency of n, you have to actually be sampling at 2 times n to capture the actual shape of the waveform. We need an extremely low signal-to-noise ratio, so we want a low noise floor. And we want high fidelity, so it can't be like a 4-bit analog to digital conversion. It'd be nice if it was 12 bits, but even 10 bits might be usable. We want to know that we can communicate over interstellar distances. We want to be able to communicate at their gigabits, not kilobits or fractions of a bit. We want minimal artificial interference. So when we find out that gravity waves works or tau neutrinos works, we want to know that the particular frequency that we're modulating and demodulating at does not have any natural sources from, let's say, reactors or particle accelerators, or in the case of gravity waves, from building mass dampeners, colliding vehicles, fully loaded semis stopping, or freight trains stopping. So what would be the behaviors of advanced communication? I'll just call it advanced communication, be it gravity waves or tau neutrinos. If you're actually modulating and demodulating using advanced communication, existing electromagnetic spectrum receivers would be deaf to the signal, because you're not communicating in a principle that they can detect and demodulate. So if you were communicating using advanced communication, no radio receiver on Earth would be able to detect your signal. If all the advanced civilizations off this planet communicate using advanced communication, that might explain why we've never heard a signal from them. They've never transmitted in radio to our very narrow EM-only ears. So it could be that once we start communicating using advanced communication, we could find that there's a whole universe out there already communicating using gravity waves or tau neutrinos. So that might be a pretty quick answer to your Fermi paradox. We already have all of the back-end signal processing we need. So the digital signal processing, like the algorithms in your mobile phone, the processors in your mobile phone, those things can be reused and repurposed. And the algorithms, fast Fourier transforms, all that stuff would be meaningful. Even though we're not using electromagnetic spectrum, it's still signal processing analysis. We might have to do some tweaks for energy levels or frequencies, but we can reuse all that stuff. And we'd be able to receive signals passing through the Earth or the Moon. So think of the deep space communication network that NASA has right now. It has 3 stations spaced 120 degrees apart on the Earth because the Earth rotates. The antenna has to be pointed directly at the source because we can't receive through the body of the Earth. Well, if we were using advanced communication and those signals can pass through dense bodies like the Earth or the Moon, put your receiver anywhere you want it on the planet. You'll be able to communicate. And you should be able to transmit gigabits across billions of miles without degradation, because the background electromagnetic radiation wouldn't be interfering with you. Okay, so once you have this ability, once you've got a basic tool to work with, what would, how would it be applicable to what we do today? Well, there's considerably less artificial interference from electromagnetic radiation radio sources. We can communicate over interstellar distances without giving up on our gigabits. And if it were available, even though it costs a lot, we would start to use it quite, widespread. If you think back to the early days of satellites, solar cells were horribly expensive. The Vanguard satellite, I think, had 3 solar cells on it. The solar cells were produced by contractors under clandestine contracts with the CIA through the Department of Defense. So if it has a meaningful purpose, you can spend a lot of money on technology that is nowhere near commercially, economically viable yet. So if we can find a way, if physics will allow it, to do advanced communication, it may start out as clandestine projects for communicating with, submarines or something. Remember, there was a military program that was clandestine for submarines deep under oceans to communicate through the crust of the Earth at low frequency radio waves, right up until whales started getting ear bleeds from it. So yeah, they can spend a lot of money on things the general public is not aware of. But you've got to spend the money, do the research, otherwise advanced communication might never happen. But once we start uncovering the science it takes to do it, the technology it takes to do it, we may find that dark matter, dark energy, and the source of gravity all become matter of cake, easy as pie. Now that we have from the first presentation, infinite source of power, from the second presentation, we have infinite source of propulsion. Now we have the third presentation, infinite source of communication. What are we going to do with all that stuff? So these things will be driving themselves into unimaginated applications, kind of like when the guy came up with the first ruby laser and said, what's that good for? I can punch holes through Gillette razor blades. And now what do we use lasers for? Tweezers for moving viruses around in electron microscopes. So, what it starts out as and where it winds up is two different ends of the spectrum. Oh, but not the electromagnetic spectrum. But once we can do this, we may find there's a lot of people out there already talking. We just don't know their modulation techniques. And then we don't know their languages. We don't know their encoding systems. Not everybody speaks in ASCII. Remember, at one time, IBM spoke in a thing called EBCDIC. So just the encoding of characters, once you get rid of all the demodulation, just the basic how you communicate, even in a different language, the letters you're using, that could be different. Maybe a whole lot of decoding that we need. So we're going to need them with our quantum computers. So now that we can pretty much do anything we want, what's next? Well, now that we have our friends out in deep space and we can communicate with them or at least receive from them, how do we get from here to there without going through all that time lag distance stuff? And that'll be the next presentation. We'll talk about getting from point A to point Z without traversing points B through Y. And if you want a kind of example of what I'm going to be talking about, in the Marvel universe, there's a thing called a sling ring that the users of magic use to open portals to go from point A to point Z without going through any of the B to Y. So I won't be talking about sling rings directly because that's movie magic, as the saying goes. But I will be talking about, if you want the closest approximation of what I'm talking about, it's not wormholes. It's not stuff from Dune. It's not transporters. It's closest thing to it would be a sling ring. So look at that. But that'll be for next time. So in conclusion, this is a series that solves problems through the application of technology. There's a lot of industries that are making good money on modulation of the electromagnetic spectrum that if you came up with something new and different, they'd have to go spend startup money again, and they don't want to do that. So there's a lot of shortcomings to modulation of the electromagnetic spectrum. And if you want things to progress, you got to get past them. And you're not going to get past them by punching your way through them. You got to think creatively. But once you do that, you may find that there's a whole new source of revenue for companies that are new or for companies that are established to make new revenue. There's going to be significant cost research for advanced communication. That's best done through government investment, maybe CIA investment. Like I said, deep water submarine communication without whales getting ear bleed. Once you figure this out, you may have to set aside certain frequencies for advanced communications. And, you're going to need governments to administer that stuff, international agreements. But once you're doing this, that means for all of the existing EM folks, there's going to be a huge paradigm shift. How come nobody wants radios in their mobile phones anymore? Because we're using gravity wave communication? Oh, well, all the radio folks better turn too. So the companies that make the radio transmitter receiver chips that are in your mobile phone, if they're not in on the new wave bandwagon, yeah, they may go disappear. It's going to take a lot of investment to improve transmitters, receivers, whatever we use for antennas. Maybe we need large arrays, big government approvals to that stuff. It's more likely small firms would displace entrenched firms, as the small guys are usually the ones that work with the government and then break out, get a couple of patents, and then corner the intellectual property. So if advanced communication becomes personally affordable, then maybe there's trillions of dollars as soon as possible in the newfangled communications infrastructure. Think about how many billions, with a B, were spent to get 5G just to where it is today. Well, when you have a new communications technology that's truly cutting edge, not a rehash of what you already have, there may be many trillions of dollars that people can spend on it. Remember, right now, they're making software changes to existing mobile phones to be able to communicate with satellites. So that's still using electromagnetic communication. They're just tweaking the software and the hardware a little bit to make them more powerful with the same amount of energy and more capable to receive a lower amplitude signal. Once we have these capabilities, we may be communicating with a lot of new friends way out there, or at least start by receiving the signal and going, I think there's intelligence in that signal. We'll get a new wow. You know, the wow signal? We'll get a new wow. But after we learn to communicate with them on a two-way basis, the next step would be, now that they're friends, let's go visit our friends. But they're thousands of light years away. It would be impractical to do that on a human lifespan. We need to go faster. But if we get rid of the fast part and just go, we need to be there, that's what we want. So we'll talk about that next time. And some links for those who want to do more research. Okay. Comments? Did I break the laws of physics too dramatically?
Very excellent presentation.
Yeah. I just think these are new things that we're not taking into account the value of them. If we can just find a way to create them on demand reliably with good flux and then switch them on and off, we can modulate them. Once we can modulate them, that becomes a mechanism for communication. And once we can communicate bits, we can communicate bytes. And once we have bytes, we have voice, video, data, all of it comes along for a ride.
And matter.
Yeah. Well, I will not get into things like replicators and transporters, because I do have to, hold up my Heisenberg uncertainty certificate.
So there's always that.
Oh, no, there isn't. I watched a video this week from Sabina Hassenfelder, of all people, say, we found a way where we can detect without destruction.
Okay.
Think about it this way. Every means we have of detecting an energy signal is by photons being converted to electrons, and then we use an analog to digital converter to convert the electrons into a digital count. Well, when you do that, you just lost your signal because you consumed it in order to read it. And what they found out was, well, the absence of a detection is the presence of its opposite. So if you were looking for a signal to come your direction and you don't detect it, it means the signal is going the opposite direction. So the absence of detection becomes detection without destruction. And I went,
charge holes, and
it's simple like p in electron semiconductors. That's just like a eureka moment, as the absence of something means the presence of its opposite.
Yeah.
So for all those people that are talking about Fermi paradox and saying the absence of a detection means the absence of a source, no, maybe they're just using something other than electromagnetic communication, and the absence of a detection is the presence of a different kind of source. So advanced communication. My head never hurts doing this stuff, but I have a lot of fun doing it.
Yeah. So I think in the case of trying to modulate gravitational waves, we are not too close from doing that, because right now at this moment we are only just observing, and the ones we are observing, the wavelengths are so huge that like they are almost close to kilometers size waves for you to observe.
The initial gravity waves we detected and peer review confirmed are very long and very low frequency, but they're high in amplitude. That's LIGO and Virgo. Look at the current generation of gravity wave detectors that are coming out of the UK. These are desktop size. The amplitude goes way down, the frequency goes way up. Those are going to be practical for gravity wave detection at the next step. And it's going to make, here's something that NIQuest should teach you, which is if I can detect a higher frequency reliably, I can also detect a lower frequency. But if I can only detect a lower frequency, I am unable to detect a higher frequency. So once we have higher frequency gravity wave detectors, LIGO and Virgo become museum exhibits. That's just the nature.
And then that would be awesome. But I find how would we modulate gravity?
We're already doing it. We're just not doing it in a controlled manner. Like I said, mass movers in the tops of tall buildings are masses moving back and forth, not with a defined frequency and regularity, but they are moving masses. And once we have a very, very low amplitude detector and a very high frequency detector, I think we're going to start to see a lot of artificial gravity waves that are just in our everyday life that because we can't detect them, we don't know they're there. The same as radio frequency interference. Until we could start detecting, certain ranges of microwaves, we weren't interested in radio astronomy. But once we were interested in radio astronomy, we went, how come at these particular frequencies, we're always getting a signal and it's when we point the antenna up? Well, there's natural radio signals that already exist and have existed for billions of years that we never knew existed until we created detectors in that frequency range that could pick them up. So science and technology repeats themselves over and over again.
Yeah.
So
and not too long ago, we didn't even know we could capture gravitational waves, and now, as you say, that is the new shorter wavelength, desktop size. I haven't read those, and that's amazing because it was I think it was 5 years ago, right?
Yes. 5 years ago was the announcement of Virgo and LIGO peer confirming each other's results. And it was very, very massive deep space, but in our galaxy, basically neutron stars fast orbiting one another, and the snap at which they collapsed into a black hole was the gravity wave we detected. So think about the level of mass movement in space-time needed to resulting from that level of energy exchange. And that was the first time we ever detected gravity waves.
And improve the gravitational part of the relativity theory being proven 100 years after the publications. It's what?
Sometimes the postulation predates the technological advancement needed for the detection. But then again, there could be other things in the universe besides gravity waves and neutrinos that we have yet to discover.
Has it been discovered yet how quantum entangled particles communicate with each other?
No.
So that's an instantaneous communication, no matter how far apart they are.
You mean as
that is so
Einstein referred to it spooky action at a distance.
Yeah.
At a distance.
Yeah.
That is
That
what,
is so freaky.
that we
But-
have
but-
to go into that.
But you know why we can't use those for communication at the moment?
Why?
Well, you
Because
have to slide out together.
the entanglement is not always deliberate, and the duration of existence of the entangled particles aren't long-lived.
Yes.
So-
Okay. Yeah.
So it's
Oh.
once again, we detect, actually we postulate, we create technology to detect, and once we detect, now what are we going to do with it? Well, we're going to use it for communication. Not so fast there. You've got to be able to create a high flux, reliable on demand, switchable source of these things. Once you have that, now you can do all you want. So if you just created out of billions of particles, you created 2 particles that were entangled, and then somehow you managed to split those particles apart, and then you affected one and it affected the other. You have to be able to do that at very high frequency, reliably over a long period of time, and they just don't have that yet. So
Okay.
when you
I
see all
think-
this stuff,
Diane has got her thumb on the pulse. It has, if we are going to communicate over galactic distances, we cannot be relying on something that moves. We have to come up with something else.
Yes.
well, maybe we'll combine next week's presentation with advanced communication. You
So
open
the
a hole
whole-
between 2 points and you communicate.
Yes, that's
The whole idea of space-time is that, like, the speed of light, of the speed of things that are limited to the speed of light in space. And the idea to move faster than light is that you're not moving in space.
Right.
You're just there at the same
Yes.
time.
right. That is where the breakthrough has to be.
And that's what we're going
Yes,
to talk about next
exactly.
week.
Yeah.
And there are people actually working on it, believe it or not.
Because when you say that's the speed of light, that's the speed of the limited of the speed of the universe. What you mean is that's the limit of the speed in space-time. So if you can fold space-time, if you can, find a way to circulate space-time and put together one part of space-time together with the other with some kind of, technology, then you basic teleporting without, wasting time. You
Well,
were just there.
Teleporting conjures up things like matter disintegration and reintegration. And
Yeah, but
Yeah,
what
no.
I mean is that you're folding space-time,
Yes.
then you can be here and there.
Yeah.
Like in a moment.
yes, there's
And
no
then but
tunnel
if
travel
you have
time.
to move through space, the speed limit is the speed of light.
Yes. Here's an analogy. In the Earth's atmosphere, what's the fastest that an aircraft can move? At what point does it become impractical to try and move any faster? Well, when the molecules of air are striking the aircraft with such force that it melts the aircraft. But, we can get to, high single-digit Mach numbers in the Earth's atmosphere. But if we want to go any faster, we have to go outside the Earth's atmosphere. Speed didn't change. Our ability to have enough propulsive force to move that fast didn't change. We changed the medium we're moving through. So if the speed of light is the fastest that a photon going from point A to point B can move, because that's the nature of the photon, why are we still using photons?
Yes, right.
Yeah.
It's got to be something else.
Exactly.
Yeah.
And there you have another example of Fermi paradox blown away, as in, as soon as we figure out what the other way of doing it is, we may find out, oh, there's all kinds of people out here talking.
Yeah.
There, as soon as we find a way to open a point between, 2 points in space-time and just step across, we may find that there's a lot of other people knocking on that same door. I want to say people, but sentient beings
Sentient beings, yeah.
knocking on
much
the same
better.
door going, hey, I'd like to come in, but it would be unintelligible because a different creature is speaking a different language with
Yeah,
a
they
different
probably look
language.
just like us. Yeah.
I think that's the key, is that the universe is not going to be so bizarre. Think about how many different human forms there are on this planet, and they're all the same. Tall, short, different eyes, different noses, different skin colors, everything different, and they're all called human.
Linguagens diferentes,
Different language.
different languages.
Yeah. See, you were speaking in a Latin derivative so I could understand it.
We should learn how to talk to the fish.
Yes.
Well, the question there is, we know that whales and dolphins exhibit sophisticated communication. A goldfish going bloop, bloop, I'm not sure is sophisticated communication.
How about birds? They can make formations. How do they do it?
They can use tools. They can create tools. I think if you could find a way to actually communicate with certain species of birds, you'd find that there's a lot on their mind.
Well, I talked one when I was a child.
Yeah, but
I had a parrot.
You didn't talk to it. It learned how to talk with you.
Yes.
We've got to learn to talk in their language.
Yeah.
Which, who knows, theirs may be telepathic and ours isn't.
I think Loro didn't know how to speak parrot because he was
Been around
born,
humans
he
too
was
much?
a baby in the middle of humans, so I
Well,
don't think Loro speak parrot. I think
there
Loro just spoke Portuguese.
yeah, there was that ape that was born and raised amongst humans, and they taught it sign language, and they wanted that ape to go teach other apes not born in that
It was an
environment,
orangutan.
yeah, sign language, and it couldn't because
Gorilla.
it didn't understand orangutan.
That
So
was a
what they
gorilla.
did was they took one that existed amongst a group, and they would bring it out of the group and put it back in the group. And yes, it attempted to teach the others sign language, and that worked a little better. Not 100%, but you could see the others doing the basics of signing. So they created their own modified form of sign language that, who knows, might have actually been more efficient. Reminds me of Colossus, the Forbin project, when Colossus and Guardian had communicated all known science and math to each other using human speak. They created their own binary language of computer to computer speak, and then humans could no longer understand them.
And they turned off the thing because they got freaked out.
Yeah. Disconnect. You forgot, we control your nukes.
Yes. Well, there was a very intelligent parrot. His name was Einstein, and they were training the parrot, and then it was his birthday or somebody's birthday, and they gave the parrot cake, but the parrot didn't have he didn't know the word for cake, so he figured out a way to ask for more cake. He wants sweet bread.
Oh,
It's like, what? You're
I-
making phrases, you're doing analogy. That's impressive.
I've seen that. There's some species of dogs that have been trained to use a symbolic keyboard, and they would put words together that they weren't taught. Kind of the same sort of thing. I think there is abundant avenues of communication with the other species on this planet that we're just not taking seriously enough because, well, they're not speaking the King's English, so they must be dumb. No, you're dumb for not being able to communicate with them.
Well, and I have, for instance, observed that the wild birds in my yard have certain speech when they see a cat walking below. I know exactly that sound. And if there's some other interference, it is like they have a different sound. And I can tell exactly afterwards when I hear this is what they meant.
Yes.
It certainly works.
They did a study of prairie what do they call them? Prairie voles. The little critters that bury around in the desert areas in sand. And what they found was there was different chirps that they would make as completely recognizable signals. And when that signal was heard, the entire
Everybody
population
vanishes.
could hear it all at once. So
Yeah.
if a predator came in the area, they could tell what kind of predator it was based upon the chirp. And if it was a no threat kind of predator, they would still pop up out of the holes and look around just to keep on lookout. But if
Exactly.
it was a ferocious competitor, one chirp and they're all gone.
You know.
We don't, but they do.
Oh yeah.
Okay. Hey, I got us in under the wire. Okay, I'm going to stop recording.